do an evaluation of the critical Euler buckling load of a 14 by 132 column. We're given in this problem that we have a W14 by 132. It has a length of 20 feet and a K value of 1.0. And we were also told that we have no stiffness reduction, which means that we use EI as opposed to EI star, which we will cover in another video. The first thing that we're going to need to do for this problem is we are going to need to find our moment of inertia values. If we open table 1-1 in our AISC manual, we'll find that IX for a 14 by 132 is 1,530 inches to the fourth, and our IY value is 548 inches to the fourth. I should also have clarified that Kx and Ky are both equal to 1.0. They are pinned in both directions. So if we want to do our PE, our Euler buckling load, often referred to as PE1, we're going to do this in the x direction first. We have pi squared times 29,000, which is the modulus for every structural steel. We have 1,530. And our effective length is KL squared, which is equal to 20 times 0, or 1.0 squared. But that's almost the case, right? Because everything else is in inches here. So actually what we need to do is we need to take this and multiply by 12, because this will make all of our units consistent. Take this entire thing and square it, and then we are able to compute this critical buckling load. We take pi squared times 29,000 times 1,530 divided by 240, which is going to be 20 times 12 squared. This is going to give us 7,602.67 kips. These numbers are often very high, so this really isn't too unbelievable. If you want to do a unit check here, you have KSI times inches to the fourth divided by inches squared. And that will give you, pardon me, because this is inches. KSI is kips per inch squared. And this is going to leave you with kips. But we're not done yet, because we have to check how this is going to perform in the y direction. So we're going to do the same equation, but now we have to use our value in the y direction, which is 548. And we have the same effective length. The pinning situation was not any different here. So 1.0 times 20 times 12 squared. All of this squared, technically. We can go in, all we have to change here is our moment of inertia. We are going to get 2,723.05 kips. And based on what we're seeing here, this is going to control because it is way less. And this is a good reminder, working through this, that whenever you're looking at any sort of buckling stress, any sort of critical buckling load or Euler buckling load, you want to look at the weak axis here, because your weak axis is going to tell you what actually governs. The weak axis is always going to control how much load it is actually able to take on. So in this case, we have 2,723.05 kips, and that will govern over the 7,602.67 kips, because ultimately when you're talking about an axial load, the column has to bear that in both axes. So this lower load is what will govern the situation. Hope that you guys found this helpful.